Welcome back to Columbia Physics Preceptor Television. Today I will be giving an example introduction for the second optics experiment, the one concerning thin lenses. Welcome to class. Today we'll be doing an investigation that looks at optics again, only this time instead of looking at general principles of optics, we'll start to look at applications. In this case, we'll look at how thin lenses work. You may have seen lenses. If you wear glasses, you may see them every day. But in talking about lenses, really all lenses can be described by one parameter. That is the focal length, which you'll usually see written as simply a lowercase f. Lenses usually fall, at least in our investigations, into two different categories. There are convergent lens or convex lenses. They're called convergent because they make rays of light which enter the lens parallel to each other, make them converge onto a single point at the focal point. All convex or convergent lenses have a focal length which is greater than 0 or positive. The other kind of lens is a concave lens or a divergent lens. Divergent lenses have focal lengths of less than 0. For our investigations, we'll be mostly looking at convex lenses. You can describe the way light passes through a lens simply by remembering Snell's law, or the law of refraction, which you investigated last time. To do this, we use what are called ray diagrams. This is simply a graphical way of tracing out the path light takes as it passes through a thin lens. Here we have a lens, and we can say that it has a focal length given by this distance. A lens always has two focal points, one on each side of the lens, at equal distances, if my drawing is good, away from the center of the lens. We can then place an object, here represented by an arrow of a certain length O, away from the lens, and then trace paths of light through the lens, sticking to three different rules. The first rule is that a ray of light coming from an object and entering the lens at a parallel direction to the main axis will be refracted such that it goes through the focal point on the other side. Likewise, a ray which goes through the focal point on the near side of the lens will then be refracted such that it exits the lens parallel to the main axis. Finally, the third rule is that a ray of light passing through the center of the lens along the major axis will not be refracted at all. It will simply pass straight through. And if your drawing is good enough, you should have all of the lines meet at a single point on the other side. This is what's called an image, which we can denote by length I. Now here my drawing is a little bit skewed, so I is slightly shorter than it really should be. The image we can parameterize the location of the image and of the object using what's called the thin lens equation. There's a derivation of it in your lab manual, but here I'll just write it down. The thin lens equation says that if the object is a distance s away from the lens, and the image is a distance s prime away from the lens, then s and s prime can be related by saying that the sum of their reciprocals, that's 1 over s plus 1 over s prime, is equal to 1 over the focal length. It should be noted that by taking s and the focal length, by knowing those ahead of time, you can predict s prime, the location of the image. The image can fall into two different categories. The first, as we see here, is called a real image. This is when s prime is greater than 0. The other case is called a virtual image. This is where s prime is less than 0. A real image you can project onto a screen, and you can say, make another focused image. A virtual image, you cannot do that. Now today, I should also note, with lenses, you may have heard of a term called magnification. This is simply the relative size of the image and the object. We can describe it using the letter M. And while normally it would be the size of the image over the size of the object, we can also parameterize it using S and S prime. In fact, the magnetization just comes out to be S prime over S. Today we will be looking at 4 methods for measuring the focal length of a lens. The first one is rather easy. It just uses the fact that I stated before, that a real image can be focused onto a screen. What you'll use is the overhead fluorescent light bulb. It's far enough away from any experiment happening on the tabletop that the rays of light are somewhat parallel. You'll then run those rays of light through a lens, and they should focus onto a point, a distance, little f, away from the lens. What you'll do in your experimental situation is have a small screen that you can move back and forth along an optical bench and find the place where the image of the overhead lights is focused onto that screen and is a clear image. This will then give you a value for little f. You should also estimate what the uncertainties on this measurement are using either the granularity of the ruler or some human judgment factor, which you should estimate numerically. The second technique for measuring the focal length is a little bit more complicated, but should yield a more accurate measurement. In this case, we'll start with an optical rail. At one end, there will be a light source given by a small, actually fluorescent light bulb. This light will shine through a screen which has in it a small opening with a wire mesh inside, which you can use as your source object. The light will then pass through a lens, and by trying to place the lens a distance f away from the original source, the original screen, the light that comes from this source should exit the lens in a parallel fashion. You'll then place a mirror on your optical bench, which will reflect those rays of light. They'll then go back through the lens and be focused onto the screen. You should see an inverted but focused image of the original object on the screen. This will happen, or it will be in focus, when the distance between the screen and the lens is the focal length f. In the third setup, you'll simply modify your experiment here by taking away this mirror and putting a viewing screen. You'll then want to place the lens at a distance greater than f, away from the original screen and the object, and try to move it such that you can focus the image onto the screen. By varying s, I should say this is s, and then this would be s prime. By varying s and s prime, you can actually make a plot of data points, plotting 1 over s and 1 over s prime. These should lie along a line that looks something like this. And by finding the intercepts of that line with the two axes, this value will give you 1 over the focal length. And again, you can estimate uncertainties based on drawing a line and finding a best fit to this data. Finally, for the last method, it's slightly more complicated, but it should give you as good a result as the other ones. In this case, you'll place an image. Here we won't be using a light source, but instead a small pin, actually inside the focal length f of the lens. This will cause you to see, as you look through the lens from this side, a virtual image. The virtual image should appear to be much, much bigger, but also farther away. What you would like to do is match up a second pin, which we would call our reference pin, from another optical rail, and see where the reference pin lines up with the virtual image such that there is no parallax. That's as you move your head, the image and the reference pin should stay in the same place, lined up with each other. By then comparing your data again and drawing a similar plot as to the one before, you should be able to find the focal length of the lens. Some of these experiments can be sort of tricky, especially with aligning everything such that the light reflects and refracts and you get a nicely focused image in the proper place. But with patience, you should be able to get very good measurements with good uncertainty values for the focal length of the lens. That's about it. Have fun.